Yeah, okay, well, thanks for coming and spending your Thursday lunchtime with me. I'm going to be talking about how wind turbine wakes break down, and this is work I'm doing as part of my PhD in the Department of Aeronautics. So the talk is basically going to be a bit of motivation for why we're doing the work we're doing, some background theory. I'll go through the method that we're using quickly, and then the results are in two parts. So a laminar flow kind of investigation, which has its own setup and results, and then some preliminary results with the full turbulent boundary layer. And again, that's got a bit of setup and results, and then the conclusions. So we need to really increase our wind energy output to meet the energy demands of the future. So the UK's government has a plan to reach net zero by 2050, and wind energy is a large part of this. So they want to quadruple offshore wind capacity by 2030. So that would be 40 gigawatts of offshore, including 1 gigawatt of floating wind. And in order to do this, we need more wind turbines, larger wind turbines, and we need to improve the efficiency of wind turbines. So one of these is increasing the size of wind turbines. The larger a wind turbine is, the more power output the more power it can generate. But this has its own problems as well, because the larger a wind turbine is, the higher up in the atmospheric boundary layer it exists. So it exists across larger gradients of temperature and velocity and things like that. And so this changes how the wake evolves, and that in turn also has efficiency problems, because when we have farms grouped together, we need to understand the wakes and how they're evolving. One of the grand challenges in wind energy is to achieve a fundamental understanding of the aerodynamics of wakes and interacting wakes behind wind turbines. So we want to know how the wake interacts with the atmospheric boundary layer, like how is the stability affected by different inflow conditions. Also, how does the near wake transition into the far wake? And another kind of grand challenge as well as this is to improve wind and turbulence modeling. So understanding the wind flow patterns, how vortices, streaks, gusts are generated, how they decay, and what coherent structures are relevant to wind energy. So based on that, I'm trying to answer the following questions. So how are the length and shape of a wake impacted by inflow conditions? And specifically, I'm going to look at shear and thermal stratification, but I'll explain why later. What mechanisms are causing the wake to break down, and what are coherent structures in the wake, and how do they contribute to the wake breakdown? Okay. So what is a wind turbine wake, first of all? So it's the volume behind a turbine where energy has been extracted from the air, from the wind. So we see lower wind speed, so there's a velocity deficit as the wind turbine has extracted energy from the flow. And we also have higher turbulence intensities than the free stream. It expands as it travels downstream, and it also mixes with the ambient flow outside of the wake. And this is what causes the wake to recover and regain that energy. But the interaction of the turbine with the flow impacts how this energy and momentum is transferred. So the figure, you can see the incoming inflow, basically, it interacts with the turbine. Then the red line is where we have a velocity deficit, which slowly recovers as this turbulence and mixing comes in and the velocity is recovered. And we transition from the near wake field, which is really dominated by the turbine characteristics, to the far wake field. A kind of key feature of the near wake field is this helical vortex structure. So these are vortex lines, I suppose, that come off the end of the blade. So they actually are off the root of the blade in here and the tip. But what we really care about is the tip vortices, because these impact the velocity field, the way the wake expands, and the length of the near wake field. So in uniform flow, so if we had no turbulence whatsoever, in theory, this helical spiral would continue forever. So it itself does not break down. So we need the interaction with turbulence or other structures to cause these tip vortices to break down into smaller eddies. And in a wind turbine setting, this is how the near wake field transitions into the far wake. So we can actually study and look at the helical vortex stability. So there are studies which introduce small perturbations to investigate how the vortex reacts to perturbations. So the left just shows the vortex development for a three-bladed turbine. And on the right, you can see a theoretical development of a perturbation on a single vortex filament. So it's initially small, and as it travels down the helix, the perturbation is amplified. And the main instability that's actually causing this vortex to break down and the perturbation to grow is the mutual inductance instability. So this is when you have out-of-phase perturbations on neighboring vortex filaments which interact. So you can see on the left that because these neighboring lines have out-of-phase perturbations, there are these locations where the peak and the trough of a perturbation will interact. And these will be initially small, and as they start to interact, they'll grow, and as it moves downstream, the perturbations will grow and break up the helical spiral. Whereas on the right, when you have in-phase perturbations, that perturbation, the neighboring perturbations do not pair and interact, so they don't break down. Of course, if you have partially out-of-phase perturbations, this will also lead to breakdown, but less intensely than if it's fully out of phase. Okay, so it's great to understand the wake in a very idealized setup, but really wind turbines exist in the atmospheric boundary layer. So we need to understand how the properties and sort of statistics of the atmospheric boundary layer impact the wake as well. So the atmospheric boundary layer is a region of continuous turbulence bounded by a sharp interface between the turbulent layer, which is what we live in, and the non-turbulent free atmosphere at the top. We have increasing velocity as we go up through the boundary layer, which follows roughly a log law. And then we reach the geostrophic wind velocity at the top of the boundary layer. And in the atmospheric boundary layer, the mean flow is a balance of the divergence of turbulent stresses, pressure gradient, and Coriolis force. A really important factor that impacts the structure of the atmospheric boundary layer is thermal stratification. So if we have a temperature gradient. So we can use a temperature gradient to categorize our boundary layer into neutral, stable, and unstable. And these have big impact on the wind turbine wake and development. So we have a neutral boundary layer, which is our sort of base case when we don't take into account a temperature gradient. So this would occur on a, say, strong, cloudy day or at sunrise or sunset. Our unstable boundary layer then, which is also called convective, which is the red line, has slightly higher velocities and higher turbulence. And this is when we have heating at the ground. So on a warm day when the sun is heating the ground, so we have the ground hotter than the air. And then our opposite is a stable boundary layer where we have cooling at the ground. So say at night, and here we have reduced speeds and reduced turbulence. And our neutral boundary layer is the most studied in literature because of its simplicity, but it only really occurs 10% of the time. And as I said, there's a big impact on the wakes due to the stability. So in a convective boundary layer, as I said, a stable boundary layer at the top, you can see the wake is much shorter. So these plots are the velocity deficit in the wake. Well, the velocity in the wake, so the blue shows a lower velocity. And when we increase the stability to go to the stable at the bottom, we have much longer wake lengths. As well as this, the stability can impact the power output of a turbine. So we have a lower power output in stable than convective. And this is before we even take into account the wake interactions. So wind turbines are obviously often put together in farms. So we have massive efficiency losses due to the interactions of their wake. So if a downstream turbine is existing in the wake of an upstream turbine, that upstream turbine has already removed a lot of the energy and power available in the air. So we have reduced efficiency in farms. We also have extra loading on the turbines, which causes fatigue. And it's been reported that in offshore farms, there are efficiency losses of up to 40% compared to a lone standing turbine. So we really need to make sure our wind farms are laid out in the most optimal way, and that we have control strategies that maximize the total output of the farm. But in order to really do this properly, we need to understand how the wakes are going to develop, what their lengths are going to be, how do they recover in the full range of conditions that they'll experience. So based on all of that, I'm doing the research I'm doing, and I'm looking at it with computational simulations. And there's, as I said, two parts to the results. So because the atmospheric boundary layer is so complex, there's interlacing features like the temperature, the velocity, the turbulence, which all impact the wake. It's hard to understand what thing is causing what effect in the wake. So the first set of results is going to be decomposing the atmospheric boundary layer to study the impact of sort of simplified individual features. So looking at just a shear profile, so a velocity gradient, just a temperature gradient, and then a little bit of a veer. So that's to do with the Coriolis force. And then I'm going to start looking at the full atmospheric boundary layer, seeing if there are comparisons, if any, and seeing if I can make any links based on the simplified case. And I'm analyzing stuff with looking at the flow field and doing some decomposition to extract coherent structures. So yes, as I said, I'm running simulations, and I'm doing these with Wink 3D, which is a open source code, which is part of XCompact 3D. So it's high order, finite different flow solver for solving turbulent flow. It's highly parallelizable, if that's how you say that word. So I can run it on thousands of cores, which is important for this study because we're running really high resolution simulations so that we can resolve the tip vortices of the flow. And I have two schemes to deal with the subgrid stresses with the large eddy simulation. So the first is implicit. So we're accounting for the dissipation of the subgrid stresses within the discretization of the scheme. And the second is Smagorinsky, which is a standard explicit model, which we can use with our atmospheric boundary layer wall model. Our turbine is modeled with an actuator line method. So instead of fully resolving the blades of the turbine, which would be incredibly expensive, especially because it's a moving structure, we'd have to be meshing or adding things to deal with that. We have rotating forcing lines, basically. So we can still get tip vortices coming off the rotating lines. And as the lines rotate, we have a lookup table to calculate the forces on the blade. And then these forces are just added as a term in our momentum equation. Okay, so onto the laminar flow section. First, the setup of this. So we've got a domain of 10R by 10R by 10R for our turbine with radius R. Our turbine's placed in the midspan and height at 2R downstream. We've ensured that the domain is large enough to avoid any blockage effects, and we've confirmed that this is the case. And it's very highly resolved. So we have 51 nodes per radius of the turbine. So we can very clearly see our tip vortices in the results. And we have inflow and outflow conditions in boundary conditions in X and free slip in Y and Z. Okay, then as I mentioned, we're looking at, we're trying to see the impact of shear profile, thermal stratification, and veer on the wake. So we're trying to look at relevant ranges of these values, but we're simplifying the profile and looking at a uniform gradient. So on the left, this is expected values for a turbine study. You can see the shear ranges from about 10 to 20% for neutral and stable boundary layers. And on the right, then we're showing our profile. So we're looking at 10 and 20%. And we've also looked a little bit at an extreme 30% case. And when I say percentage, I mean the change in the velocity from the center of the turbine to +1 radius. Our thermal stratification is done in a similar way. So we would expect values just based on the left, just under 1% of thermal stratification for our stable case. So we're looking at 1%. And again, we've exaggerated this to see what happens when we go to 2% as well. the larger turbines get, the larger these percentages are going to be anyway. And then, as I said, we're looking at VIR in actually just a single case, but I thought I'd pop it in here anyway. So expected value, say, could be a change of 4 degrees per across the radius of a turbine. So that is what we're looking at as well. Then we are adding harmonic tip perturbations to perturb the flow and trigger the mutual inductance instability, so we can see how these inflow conditions affect that. So what we have is a sinusoidal force term, which is located just where the blade tips are located in our simulation. And we add this force term into the momentum equation. The key thing here is K, which is the dimensionless wave number. So if we have K as 1.5 or 4.5, and other numbers as well, but those are what we're looking at, we get out of phase perturbations because we'll have 1.5 waves of the perturbation for every rotation of the turbine. Okay, so what does it actually look like then? So this is the case with a wave number of 3/2 in uniform flow, and the plane in the background is the mean stream, is not the mean, is the streamwise velocity, and then we have vorticity contours on the front. So you can see from the velocity that there's a velocity deficit in the middle of the wake, and from the vorticity contours you can see that they're initially parallel vortex lines which start to roll over each other in these specific locations where that's hard to see when it's moving, but where the perturbations have grown and are interacting with each other. You can see that there's a slight wake expansion, and some of the velocity deficit is recovered as you move downstream, but in this very simplified case with one perturbation, there's not much. So this is the same with uniform inflow again, but we have our slightly higher frequency perturbation. So I think you can kind of see with this one, there's more like obvious locations where the perturbation has grown, and this is causing the helical vortex to break down. So this is the same setup or the same kind of results, but with 20% shear. So you can see the impact of shear here. So we have our vortex line slanting due to the increased velocity at the top compared to the bottom. So we have a larger spacing between the vortex lines along the top than the bottom of shear. So because we have our distance between lines closer along the bottom, our perturbation interacts sooner along the bottom than along the top. So we have the wake breaking down first along the bottom, then along the top. The main sort of overlapping pattern is the same, where we have these still locations where the perturbation is growing. It's a bit harder to see with shear, but yeah. The other thing we have is an increase of radius along the bottom of shear, but I'll talk about that a bit later. So this is what these plots basically compare the impact of shear and thermal stratification on the vortex footprint. So what we have here is we've cut along the top of the vortex lines, what you saw in the videos, and flatten them out. So along the x-axis we have streamwise distance. Along the y-axis we have angle around the turbine. So 180 degrees is the bottom, and then 0 or 360 is at the top. So you can see, I think, more clearly here how the mutual inductance instability is developing and causing breakdown. So we have these initially parallel lines which start to distort, and once they do, they have locations where they merge and pair. So this is the 3/2, this is the 9/2, where we have more locations. And shear has the effect of slanting the wave, so that's the sort of bend. You can see the closer together lines along the bottom and further apart along the top, and then when we get to 20%, we have much more turbulence coming into the domain that we've studied. Interestingly, though, we're also comparing thermal stratification here, which maybe is hard to see because it doesn't really make that much of a difference. So we have on each plot overlapping the impact of thermal stratification, and the only kind of small thing that's happening is towards the side, so at 90 and 270, there's a slight increase in the perturbation growth as we go from 0 to 1 to 2% thermal stratification. But apart from that, it doesn't really impact the wake length or the breakdown locations. Our inflow conditions do impact the wake area. So as I mentioned, I think wind turbine wakes expand as they move downstream. So for a so here you can see the wake boundary at 1 R downstream, 2 R downstream, and 3 R downstream for each case. When we have uniform flow, it expands radially the same the whole way around, and it gets to about 1.2 R at 3 R downstream. When we have shear, we have a big increase in the wake boundary along the bottom. So this is the 20% shear case. We've got the wake increasing to about 1.4 R. We have a slight decrease in the wake radius at the top, but it's not as big as the increase along the bottom. And with thermal stratification, we have a very small increase in the radius at the sides. So we can compare the triangle, all the triangle lines. You can see there's a very small increase in the radius at the sides, but it's by about 4% compared to the case without thermal stratification. So it is small, but it is there. Okay, so we look at coherent structures in the wake, and we find these using proper orthogonal decomposition. So this is a decomposition method which extracts orthogonal modes from the flow, and then it has them ranked in terms of their total energy contribution to the flow. So it's good to find structures that we care about, that are a large part of the flow, basically. They appear in pairs with the same energy and frequency content, and these pairs combine to form a traveling wave. So what you can see here is the first mode of the first two most dominant mode pairs, and these are very energetic compared to the rest of the modes for this setup. They take up about 80% of the energy. It's a very simple setup with just our turbine and one perturbation, so 80% of the energy in two modes is a lot, but as expected, I guess. So anyway, the first mode is the helical spiral. So this is due to the turbine itself. And from further analysis, we've confirmed and found that this mode itself is not bringing in any turbulent energy from outside, so it itself is not causing the wake to break down. And then on the right, you can see what we call the mutual inductance mode, but I suppose it's from the mutual inductance instability. So you can see for this case, which is the 3/2 case, there's 3 lobes, and these relate to each a half wavelength of the perturbation. If we had the 9/2 case, we see 9 lobes. And we find this mode does cause breakdown, so it is bringing in turbulent energy from outside of the ambient into the wake and causing it to break down. After this, we have much smaller energy modes that are harmonics of the helical spiral and the mutual inductance, and other energetic turbulent modes. Also, I should mention, when we add shear and thermal stratification, the structure of the modes is the same in terms of it being a helical spiral and a mutual inductance, but the shape of it maps to the shape of the wake. So we have slanting when we have shear, and very little change when we have thermal stratification. We also calculate how our perturbation grows at different points around the wake. So we do this using Fourier to find using the Fourier mode of the frequency we're looking at. We can find the maximum of the magnitude of this at each downstream location, and then see how that grows, the gradient of that growth. So this is for our 9/2 case because there's more points of measurement, so it's a bit more interesting. So on the left, you have the POD mode with the 9 lobes. And then on the right, you can see how each lobe is growing for each inflow. So when we have shear, this is the 20% shear case, we have much larger growth rate along the bottom than without shear. A small decrease in the growth rate along the top, and we would expect that based on the shape of the wake. And we find that with thermal stratification here, we have a slight increase in the growth rate at the sides, even a smaller increase in the growth rate at the bottom. And again, this I think makes sense because when we were looking at the overlapping vortex filaments, we did see that there was a very small increase in the perturbation growth and the breakdown overlaps. Okay, just to look at something slightly different but kind of similar, we're using a different method to force our trigger to turbulence. So we have a dynamic pitch control scheme, which basically the idea is to pitch the blades at a set frequency. And this is the now method that's adding the disturbance to the flow. So this is based on work which are showing that there's at least potential for this to improve wake recovery. And the frequency here is actually chosen to utilize natural frequencies in the boundary layer to enhance mixing. So we're using that frequency, but we don't have it in a boundary layer here. We're just looking at how the vortex lines develop and things. So we're pitching blades with a sinusoidal term. And now our frequency is about 1.1 of the angular frequency. And I'm just going to quickly show basically what it looks like, and then we've extended the parameter space, but the main conclusions for inflow are the same here. So here's the vortex filament pattern with the pitch control. So as I said, we have a slightly different frequency, so we're not completely out of phase anymore. But you can still see the same thing of the vortex lines starting to bend and overlap, but they're not as clear peak and trough sort of merging points. Our forcing level here is stronger, so it's actually happening sooner, but basically we have similar things, and then these kind of really nice vertical, I think, overlap locations. As I said, we're extending the parameter space, so we tested a 30% shear, and we found that increasing from 10 to 20 to 30% just increases this effect, so our wake gets even longer along the top and shorter along the bottom. And we also looked at the wake. So VAIR doesn't really impact the wake length, but importantly, it does skew the wake. So we have a change in the wake area. So we have these maximum radiuses found at, well, along this line, and then minimums along this line. The POD modes for the dynamic pitch control case are pretty fun, I think. So we have three dominant modes which are related to the pitch control. So we have this first really lovely, like, clean pulsing lines one, which has the same frequency as the pitch control. Mode pairs 2 and 3 are harmonics of this, and then our fourth mode pair is our helical spiral. Again, modes pair 1, 2, and 3 are bringing in turbulent energy from the ambient, so the pitch control is doing its job. It is causing the wake to break down, and the helical spiral is not doing that. Interestingly, with this case, these modes are overall a lot less dominant than the ones from the harmonic tip perturbation. But we found that the smaller, less energetic modes have about 2/3 are doing about 2/3 of the work of bringing in turbulent kinetic energy. So we still do need to pay attention to those smaller modes. Okay, so far we found that our mutual inductance instability does cause breakdown. I mean, we knew that, but we've confirmed it. We can utilize this in dynamic pitch control schemes to trigger early breakdown. Shear lengthens our wake along the top and shortens it along the bottom. Thermal stratification alone does not lengthen the stable wake. VAIR also doesn't, but it does skew the wake. And it's the interaction of the turbine with this forcing or control that we've added that gives these structures that break up the wake, not the turbine itself. Okay, so as I said, this is a very simplified case, and it would be nice to see if we can use the sort of what we've learned and some of the analysis techniques and apply them to a full turbulent atmospheric boundary layer. This is work in progress, so I'm just kind of introducing the concept. First of all, we do have a slightly different setup. So here we're modeling a full-scale turbine with a diameter of 126 meters. Its rated speed of 11.4 meters per second. So we're trying to have it run at rated speed. And we are modeling a tower and a nacelle here. Our domain is a bit different too. Of course, we now have our turbine placed in the bottom of the domain. The tower is along the floor, or the base is along the floor. We have a domain of 12 diameters by 8 by 8. So we have a height of about 1,000 meters. And we have a precursor simulation of the atmospheric boundary layer to provide the inflow profile. And we're slightly less resolved, 64 nodes per diameter, so it'd be 31 per radius, 32 per radius here. But we have confirmed that this is still an okay resolution for what we want. So as I said, we want our ABL, atmospheric boundary layer profile, to give us approximately the rated speed at the turbine. So we're running it at rated conditions. So we have that, we have quite strong shear, and we have turbulence intensity of about 13% in the Streamwise direction. Sorry, at the turbine hub location is what I meant. So this is a plane of the Streamwise instantaneous velocity. So as you can see, it is way more turbulent. There's so much more going on than in our simplified case. You can see this is the location of the turbine here, so you can see that it does move. There is a velocity deficit behind it, but it is in an instantaneous setup. Difficult to see the wake boundary, difficult to see what's really going on. Yeah. And this plot here shows the vorticity contours on top of now the mean velocity. So you can see in the background, the mean velocity is much tidier than the Streamwise, so we can see the wake shape and the deficit in the wake, which fades out. But I think interestingly, the vorticity contours just look completely different. So we can see some trace of the helical vortex for sort of three or four rotations, but already it's immediately broken up. And then by the time we get to about 1 radius downstream, we have no kind of visible sight that there was ever a helical vortex there. And it breaks up, and the vortical structures of the wake are interacting with the atmospheric boundary layer, and it's much more difficult to see what's going on, basically. So it's much harder to study this in terms of vortex breakdown, but we are trying to think of how we can look at it still and get some clean data out. So this is again the first kind of look at this, but we're looking at 2D POD mode, so looking at coherent structures but in 2D, and this is because the data is much noisier than the laminar case. So if we have 2D snapshots, it kind of takes out an extra degree of freedom and complication. So here we have to do some pre-processing to remove the wake from the boundary layer. So first we subtract the mean boundary layer flow, and then we remove any values from outside the wake boundary. So any values under a certain deficit, we just get rid of, so we isolate the wake. We have found some quite clear structures. So we have a trend from the larger scales to smaller scales, which makes sense because with respect to energy, we often have kinetic energy. The kinetic energy in a flow decreases in scale. And we have the first mode is actually just the mean field. We have mode 2, which is a dipole structure. Mode 3, which I think is a tripole asymmetric thing. And then 4 and 5 are both quadrupole. 6 is rotational, and 7 and 8 have 6 poles. So based on this, most of these are actually symmetric. So we could say that the wake here is largely uncoupled from the boundary layer due to mostly rotationally symmetric modes, but it's not perfect. I mean, this I don't think is symmetric. But yeah, basically this is our first kind of look at trying to do this, and we want to look at a lot more different locations, but it is promising that we will get some good data. So to conclude then, we can look at the impact of shear, thermal stratification, veer, and perturbations on the wake vortex breakdown in a simplified flow. We do find our mutual inductance instability causes breakdown, and we can use that in control schemes. I think the key takeaway or the key result really is the impact of thermal stratification, because it doesn't lengthen the wake on its own, which is unlike the stable atmospheric boundary layer, where we find that this temperature thermal stratification that causes the stable boundary layer leads to really longer wakes. But it's maybe the kind of conclusion is that we do need the full atmospheric boundary layer profile there. So we need the wall stress, the stresses along the wall, so that this temperature gradient is causing the turbulence intensity to reduce. When we go into the atmospheric boundary layer, the turbulence really does complicate things and disrupts the tip vortices immediately, but we can still hopefully find some good conclusions studying this. And importantly, we really need the interaction of the turbine with the surroundings, or the blades of the turbine with the surroundings, or with the tower and the nacelle, to create these coherent structures that are actually causing breakdown. But yeah, hopefully more to come on this. I do have a couple of papers out which are mainly dealing with the first part if you are interested and want to know more. And I'd just like to acknowledge my supervisor, Sylvain, and Yorgos at NREL for helping me and supporting me through this, and everything along the bottom for giving me computational time and funding my PhD. Thank you for listening. If you have any questions, I'd love to try and answer.
You mentioned that one of the big problems with the farms now, there's a lot of the technical terms I don't get, but at least I got the fact that if wind turbines are in front of each other, they're gonna steal each other's wake.
Yeah, basically.
So how can you make wind turbine farms more efficient towards that? You told that there's needed more research to figure that out, or do we know roughly how to do that? Just space them out further from each other, or?
So there's loads of different things that are already in practice. So yes, spacing them out more, but then you have a lower power output for that bit of land. Putting them in different alignments, so you have one here, one, so they're not, so a staggered alignment, so they're not all on top of each other. Then there's control schemes which don't, so traditionally the control scheme would be every turbine just take as much power as possible, but now they're thinking, okay, we can work them as a farm a bit better. So the first row is just working at a lower rate, so they take less energy than their maximum. The second row then has a bit more. Or you can yaw the turbine, so deflect it from the inflowing. So if you have the inflow like this, you can put it at a slight angle, so then its wake is deflected from the wind turbine behind it.
Oh.
And then also, as I mentioned this kind of very briefly, but this dynamic pitch control is part of this new set of active wake control, where they're trying to actually control the wake so that the wake breaks up sooner. So if we can get the wakes to recover quicker, then by the time the wake reaches the next turbine, there's more energy from the air. But it's like, I'm looking at this from a very aerodynamic perspective. There are problems with fatigue when you have blades on your turbine rotating and things like that. So there's a lot of things to kind of consider. But if we know how long the wakes are going to be and how the wakes are going to recover, then for each site, I think you can improve, like, okay, this layout's going to work better here, this layout's going to work better here.
Sorry, I got a follow up on that.
Yeah.
Is it a common problem then in most wind turbine farms that they are stealing each other's wake?
Yes, I think so. Yeah, I think it's probably like once you've now improved the rotor design is pretty good. The thing to really get the energy, what's the word? Where the focus of the research is really going to improve efficiency, I think, is like farm level efficiency and control. So that is because the wakes are definitely interacting, and when we put them in a farm, we know they're never as efficient as what we think they're going to be, basically.
Farm level interaction would be where they're placed compared to each other.
Yeah, so just the fact that a lot of the research is done, okay, we've optimized this turbine, it's amazing, we think that this is the best place to put it, but then you actually put it in the field, and you're like, okay, why is the energy way less than what we thought? And I think it's them interacting together, but I also think it's the fact that the full range of the atmospheric conditions aren't really studied, so we don't really know how that's going to change, one, just the power output of a single turbine, but also, yeah, the wake of a turbine, and then that affects all the other ones.
Okay, so we're not maximizing the potential for those improved turbines. Could maximize their potential in terms of where we place them compared to others,
Yeah.
for the other turbines.
And there's just so much, there's so many complicating factors. Like someone else in my group is looking at, okay, if we have a hill, where do we place the turbine on the hill to get the most? So if we put it at the top of the hill, it gets the most energy, but then well, okay, I could be saying, I don't exactly know, but if we put it at the bottom, it gets a lot of energy, but then its deficit is way longer than if we put it at the top. So it gets more energy, but a turbine behind it gets less. So there's just so many factors of placement and everything. And I mean, I talked about offshore wind, which is, I think, where we're going to go as well. And then the boundary layers and airflows out to sea are much more are very different to on land. So there's that complication. And if you want to go even further, which is not what I'm looking at, but when you have floating wind turbines, so we need floating wind turbines because we can put them further out to sea, but they move with the sea's motion. So that's adding all these extra perturbations and disturbances that it's just, we just can't control or know how to optimize these things at all yet.
It sounds like pandemonium from a mathematical point of view. It's like, how do you predict that?
To add all of
the it does.
Yeah, there's some interesting studies which they start with the tip perturbation, but then they do like a rotating perturbation, or like every degree of freedom they perturbate and see how it affects the wake. And this is just, I suppose, the first most simple case of it.
Thank you.
No, well, thanks for your question.
I just had a question about
the software. I'm using Python. So I've got like, yeah, Python scripts with the data coming in, and yeah, they're messy, but yeah, Python modules to do like proper orthogonal decomposition, and yeah, our code outputs just like velocity fields. So from that, I'm working out like sometimes vorticity, but yeah, Python scripts basically.
I guess I could have another question. With the floating wind turbines,
Yeah.
are they starting to become a thing now? Are they just very experimental at this stage, or
So I think they're starting to become a thing. It's all talk, like at the wind turbine conference, it's all talk about we're going towards floating wind.
Oh, really?
But
okay.
I think it's still early days. So like the targets for wind is 40 gigawatts offshore, but 1 gigawatt of floating by 2030. So it's still early days. I think again, this isn't my total area of expertise, but I think the base now is that you put a wind turbine on like an oil rig. So it's not or not necessarily a rig, but the structure that would be used for an oil rig. So it's not a idealized structure yet for the wind turbine. We're using like pre-existing technology and adapting it to use for wind turbines. So I think there's still improvements that can be made in the structure, still things with like getting the energy efficiently back to land, and then yeah, just how are we going to control these so they don't tilt and tip over, and improve their efficiency and stuff.
Yes. How difficult are they to maintain when they're far offshore? You know, that sounds like a hassle getting out to them as well.
Yeah, exactly. So there's a lot, but I think if really we are going to have the amount of wind energy capacity that the government says we're going to have, which I don't know, it's got to go further out because we're running out of space.
yeah, right. Yeah. It's quite an ambitious goal as well. 2050, right? What do you think are the odds that we'll actually get there from a?
I don't think so. I remember, yeah, it's something like building 5 turbines a week until 2030 or something, which is just
5 wind turbines a week.
Yeah, so basically one a day. I remember meeting someone who had come up with this method to 3D print turbine blades.
Oh, yeah.
And I was like, oh, what, like, surely what's the point? And he was like, because we need to build one a day until like for 10 years in order to reach the targets, and there's no way. So it was like, there's, yeah.
That's-
So I do think sometimes the government is just like, oh, we'll do this and we'll put more money into it, but the actual, like, what has to be done
Yeah.
seems pretty ambitious, but still getting closer to it is still better than not getting anywhere, I think.
Sure, yeah, sure. Yeah, the more wind energy we can get, the better, right?
Yeah, I think, yeah, it's pretty developed energy. We know it works for our country.
Yeah.
So yeah.
Certainly a lot of wind. You, what do you think is, sorry, I have so many questions.
No, it's great.
Am I keeping you up?
No, no.
Is it, how does it compare to like solar and other green energies? What would you classify them as? Renewable energy?
Yeah, I suppose, yeah, renewable energy.
How competitive is wind compared to, say, water and solar and even gas? I've started reading a little bit about gas energy and the potential of like natural gas. That was mostly in America, that there might be lots of hidden reserves of natural gas that we're not even aware of, that we could dig into. But how competitive do you think it is compared to the other energies?
I don't know. I can really only talk in terms of wind. I think you have to take into account like where you are. So I think for us, it's got to be wind over solar, for example.
Right, yeah.
But I think that like in terms of the technology, it is a fairly mature technology, although we have these still things that we can improve on, but we know that like building a wind turbine is going to give us energy. So I think that's good, but I don't really know in terms of actual competition, but I do think the numbers show that like wind energy is often a big part of countries' schemes for renewable energy. So I do think it is up there.
One of the better options for England. Yeah.
I think so, yeah.
Yeah.
So very competitive.